In one of the previous lectures, we had discussed about the direct common tangents and transverse common tangents between any two given circles, and we had specifically considered different cases, in which one of the case was where the circles intersect each other, and given the equations of the circles, we had also told how to find out whether two circles are intersecting or not. But then for those conditions we had not given any proof. So, to be precise, what we had said was that suppose if we have two circles S1 having equation x square plus y square plus 2g1x plus 2f1y plus c1 equals 0, and another circle S2 having equation x square plus y square plus 2g2x plus 2f2y plus c2 equals 0. So, we are given these two equations, and then we are asked to find and then we said that these two circles will intersect each other if and only if the distance between their centers. So, let their centers be, so the center of the first circle S1 denoted by O1 has coordinates minus G1 minus F1, and the center of the second circle O2 is minus G2 comma minus F2. The radius of the first circle R1 equals square root of G1 square plus F1 square minus C1, and similarly the radius of the second circle S2 is equal to square root of G2 square plus F2 square minus C2. So, just given this much information, we said that if the distance between the centers, so if the distance between the centers, which is square root of, so the distance between these 2 points, which is square root of G2 minus G1 whole square plus F2 minus F1 whole square. So, we said that if this distance is less than or equal to the sum of the radius, or if it is greater than or equal to the difference of the absolute difference of the radius of the two circles. So, if this is true, so if this condition is true, then we said that the two circles intersect each other. We also said that if dO1 O2, which is the distance between the centers, is equal to R1 plus R2, then the two circles touch each other externally at exactly one point. So, this is the case where we have something like this. So, this could be S1 and this could be S2, and they touch each other at exactly one point here. So, let that point be P. So, these are the centers O1 and O2, and then we had also said that the straight line joining the centers will also pass through this point P, where the two circles touch each other. And then we also said that if dO1 O2 is greater than R1 plus R2, then the two circles do not intersect. So, this case is something like this, where we have the first circle and the second circle, and they do not intersect with each other. So, this is this condition, and then we had also said that if the distance between the centers is equal to the absolute difference between the two radius r1 and r2, then the two circles touch each other internally. So, what we mean by this is, so this could be the first circle S1 with center at O1, and then we could have the other circle S2. So, this is S2 with center O2, and these two circles. So, the circle S2 touches the circle S1 from inside, that is why we said internally at just one point P, and in this case the distance between the two centers is the absolute distance between the radius. And then of course, we also had discussed the last case where the distance between the centers is strictly less than the absolute difference between the radii, in which case again the two circles, of course, they do not intersect, and further that one of the circles is going to be completely inside the other circle. So, we have a situation like this where, let us say we have circle S1 with center O1 here, and then we have this circle S2 with center O2. So, these two circles do not intersect, and further that one of the circles S2 is completely inside the other circle S1. So, the main discussion of this lecture is going to be focused on rigorously deriving these conditions. So, we will show that the two circles, any two circles will intersect each other if and only if this condition is satisfied. That is, what that means is that if this condition is not satisfied, then the two circles cannot intersect each other. And then as special cases, we will also show that if the, and this, all of this will be proven rigorously, because we had not done that in the lecture where we were discussing the derivation of the common tangents. And then we will also show this special case where if the distances between the centers is equal to the sum of the radius, then they will touch each other at exactly one point, because when they intersect each other, they will be actually intersecting at two different points. But as a special case, when the distance is equal to the sum, then they touch each other externally. By externally, what I mean is that the two circles are not inside each other. So, for example, S2 is outside S1 and it is touching S1 from outside at this point P. And then of course, we will also show the rigorously derive this case also, where the one of the circles touches the other internally. So, let us start with seeing exactly under what circumstances will it so happen that two circles will intersect with each other. So, let us say that we have these two circles. So, and so we have circle S1 and we have circle S2, and let us say they intersect at these 2 points, and let the coordinate of one of the points of intersection be x and y. So, this is the center O1 of the first circle whose coordinates I will denote by a and b, a comma b, and O2 is the center of the second circle whose coordinates I will denote by c and d, c comma d. And of course, this the length of the straight line is the distance dO1 O2 between the two centers. So, since S1 and S2 intersect at this point x comma y, this point x comma y lies on both the circles. Now, to solve this problem, we are going to use the parametric form of or the parametric equation of a circle. So, if you remember the parametric equation of a circle, then any point, let us say x and y on the circle can be written like this. So, the x coordinate can be written as x equals to the center, the x coordinate of the center of the circle plus the radius of the circle times cos of some angle theta. So, this angle, usually this angle is the, if we draw a line through the center of this circle which is parallel to the x axis, let us say. So, this green dotted line, then theta is simply the angle taken in the anti-clockwise direction, from the x axis to this radius which joins O1, the center, with this point x y. So, this entire angle, so this angle is theta. So, then using the parametric form, we have the x coordinate of any point on the circle written as a plus r1 cos theta, and the y coordinate will be equal to the y coordinate of the center, which is b, plus the radius times sine of the same angle theta. Now, since this point x comma y also lies on the second circle S2, we can write x and y in terms of the parametric form of the second circle S2 also. In that case, x is equal to c plus r2 cosine of some other angle phi, because now the angle will be different, because now we are trying to express the coordinates of this point x and y in parametric form with regards to the second circle S2. Now, if again for to show phi, what we have to do is we have to draw a line parallel to the x axis through the center O2, and then let us say we have this radius joining the center O2 with this point x y, and then the angle from the horizontal or from the angle of this radius with respect to the x axis taken in the anti-clockwise direction. So, we have to see by what angle should this horizontal x axis be rotated in the anti-clockwise direction, so that it coincides with this radius. So, that angle is precisely this angle, so this much, and I will denote it by phi. So, then since this point x comma y lies on both the circles, so we initially express the coordinates x and y in terms of the parametric form as in parametric form with regards to the first circle, and since the same point also lies on the second circle, so we express the coordinates again in parametric form with respect to the second circle. So, x is this and y will be d plus r2 sin phi. Now, if I equate this and this, what I end up getting is that a plus r1 cos theta is c plus r2 cos phi. So, at this point, without loss of generality, let us assume that, so without loss of generality, let us assume that r1 is greater than or equal to r2. So, if r2 is greater than r1, then the same type of proof will follow, it is just that the roles of r1 and r2 will get reversed. So, with this assumption, by equating this and this, what we actually get is r1 cos theta is equal to c minus a plus r2 cos phi. And similarly, if we equate this and this, we get r1 sin theta is d minus b plus r2 sin phi. So, if r2 were to be greater than or equal to r1, then we would have written this whole thing differently. Then in that case, we should have written r2 cos phi is equal to a minus c plus r1 cos theta, and r2 sin phi is equal to r1 sin theta plus b minus d. So, and then the remaining proof is exactly similar. So, that is why we said without loss of generality. Now, we square both these equations, both the sides, and add them up. What we get on the left hand side is r1 square cos square theta plus r1 square sin square theta. So, this is the left hand side. On the right hand side, we get c minus a plus r2 cos phi the whole square plus d minus b plus r2 sin phi the whole square. Because cos square theta plus sin square theta is equal to 1, the left hand side simplifies to r1 square. So, we have this equation, and if we now expand the right hand side, what we get is c minus a whole square plus d minus b whole square plus r2 square cos square phi plus r2 square sin square phi plus 2r2 c minus a cos phi plus 2r2 d minus b sin phi. Now, this is nothing but r2 square, because cos square phi plus sin square phi is 1. So, we get r1 square is equal to, and this quantity is nothing but the distance between the two centers AB and CD. So, this quantity is nothing but, therefore, this is equal to the squared distance, sorry. So, this is the squared distance between the two centers. So, therefore, we have r1 square equals the square distance between the centers plus r2 square plus 2r2 into c minus a cos phi plus d minus b sin phi, and then we do a little manipulation here. So, just this term we multiply and divide by d O1 O2, and this becomes c minus a by d O1 O2 times cos phi plus d minus b by d O1 O2 into sin phi. Now, if we realize, we know that d O1 O2 square is c minus a whole square plus d minus b whole square. So, essentially we have something like this, c minus a and d minus b. So, we have a right angled triangle whose hypotenuse is of length d O1 O2, and the other two sides are c minus a and d minus b, let us say. And therefore, it should be, and we can in fact, it is not very difficult to show that right angle triangle here. So, if we go back to our figure, so this right angle, if we draw a perpendicular from this center O2 to this green dotted line which is parallel to the x axis, let us say this perpendicular, then this is the right angle triangle that we are talking about, because in this right angle triangle the hypotenuse is of length d O1 O2, this length is c minus a, this is d minus b, and let us denote this angle of the right angle triangle by alpha. So, we have this angle to be alpha, and therefore, c minus a by d O1 O2 is nothing but cos alpha, and d minus b by d O1 O2 is sin alpha. So, we will use this now in this equation. So, therefore, what we have is that R1 square is d O1 O2 whole square plus R2 square plus 2 R2 d O1 O2 times cos alpha cos phi plus sin alpha sin phi. So, this is using the cos A cos B plus sin A sin B formula, this is equal to cos of phi minus alpha, and therefore, from here we get that cos of phi minus alpha equals R1 square minus d O1 O2 whole square plus R2 square over 2 R2 d O1 O2. So, if we, so let us, since our main objective now is to find the value of this phi, because if you remember, the original problem was that we were given these two circles and we are supposed to find out the points of intersection. Now, since we use the parametric form, finding the points of intersection is the same as finding these angles theta and phi, because once we find theta and phi, we can obviously find x and y. but then this theta and phi should be such that they simultaneously solve these two equations. These are trigonometric equations. So, we have two unknowns theta and phi, which must be found out, and all the others are, all the other variables here are known to us, because r1 is known, r2 is known, the coordinates of the two centers a, b and c, d are also known, and that is what we have been trying to do in the last few slides. And we have reached at this point where, since everything else, so this right hand side is completely known to us, alpha is also known to us, because if we recollect, cos and sine of alpha are trigonometric ratios of known quantities. So, alpha is also known to us, and therefore, we should be able to find out phi. And once we have found out phi, we can plug that value of phi back into these two equations, and we can easily find out theta. And once we know theta and phi, we can find we know the coordinate of the point of intersection of these two circles. So, to solve this, let us draw the graph of cos of phi minus alpha versus phi. So, at phi equal to alpha, cos of phi minus alpha will have the higher maximum value of 1. At alpha plus pi by 2, when phi is alpha plus pi by 2, cos of phi minus alpha will be 0. At phi equal to 0, the value is cos of minus alpha, which is, let us say, this value. At alpha plus pi, the value is going to be, the value of cos of phi minus alpha is going to be minus 1, which is here. At alpha plus three pi by 2. So, when phi is alpha plus 3 pi by 2, cos of phi minus alpha is again 0. So, it is again here. And then let us say that we only plot till 2 pi, because it is enough, since these functions, cos of phi minus alpha is a periodic function of phi, periodicity being 2 pi, it is enough to draw the graph between 0 and 2 pi, because for all other intervals, so for the interval from 2 pi to 4 pi, the graph is going to be exactly similar. Similarly, the graph from minus 2 pi to 0 will also be the same as the graph for 0 to 2 pi. So, the graph obtained will look something like this, and then it goes to 0 here, and then minus 1, and then back again to 0 here, and at 2 pi it is basically going to complete one full circle, or one full 2 pi rotation, and therefore, this value and this value will be the same. And then let us say that, so now it is clear that if this right hand side has a modulus greater than 1, then clearly there exists no solution, and that is precisely the case where what that means is that since there is no solution, or basically there is no solution to this trigonometric equation, in that case where the absolute or the value of the absolute value of this right hand side is more than 1, which means whether either it is greater than 1 or it is less than minus 1. So, in that case, since there is no solution to these trigonometric equations, it is clear that the two circles will not intersect. So, the other case is when the modulus of this absolute value of this right hand side is less than 1. In that case, if the value is, let us say, if the absolute value is strictly less than 1, so that is the case where, So, let us say that the value is strictly less than 1. So, let us say the value is something like half. So, then to find out the solution, what we do is so let us say this value is equal to this much. So, this right hand side is equal to this much, and therefore, we draw a horizontal line parallel to the x axis. So, sorry, this red curve will only go till here, because this and this should be same. And therefore, what we see is that for any value which is strictly less than 1, it is very easy to see that there will be actually two different solutions or two different values of phi which will satisfy this equation. So, we could take any other value also. So, we could take some other value, let us say this value, which is let us say minus 1 by 4. So, if this right hand side is minus 1 by 4, then to find the solution we will draw a horizontal line parallel to the x axis, whose vertical distance from the x axis is 1 by 4, but it is on the negative side, on the negative side. So, basically this green line. So, when this is minus 1 by 4, the two solutions are given by the point of intersection of this green line with the curve of cos phi minus alpha, and those 2 points are this. So, these two ones. So, one can easily see that for any value of this right hand side which has an absolute value less than 1, there will exist two distinct values of phi or two distinct solutions for phi. And for each such solution of phi, if we put it back in this equation here, then we will get a unique value of theta corresponding to that phi. So, that will be one theta and phi pair. Now, because there are two different phis for such cases where the right hand side has absolute value less than 1, it is clear that there will be two different theta phi pairs. What that means is that there will be two different points of intersection, for example, as shown in this figure here. Now, for this case where the absolute value, so this is the case which we are dealing with right now, the absolute value of the right hand side of the equation on the previous slide of this equation. So, if this right hand side has absolute value strictly less than 1. So, this is the case that we are considering, and we have argued that in this case there will be 2 points, exactly 2 points where the two circles will intersect. But then ultimately what we want to show is that we want to show that this condition implies and is also implied by the condition that the distance is less than the sum of the radius and greater than the absolute difference. So, this is what we should get starting from here, both ways. So, if we start from here, we should get this, and this should also imply this. So, but if you want to see that, we have to go back to the equation before this equation, which is written here. So, if we again see this equation r1 square, or rather if we see this equation, the same equation again, it reminds us of the cosine formula, the cosine law. This reminds us of the cosine law, because if we remember the cosine law, what we had was that, let us say if we have a triangle with sides r2, r1 and d/O1, O2, and let us say that the angle between the sides of length r2 and d/O1, O2 is beta, then we know that cosine of beta is nothing but r2 square plus d/O1, O2 whole square minus R1 square upon 2 R2 into d/O1 O2. And this right hand side is very similar to this side, except that we have to negate this, except for a negative sign. So, if we take minus of this right hand side, we will exactly get this. So, what that means is that if we again go to our the starting slide, then let us try to see where exactly is this angle, I mean beta, that we are talking about. So, if we go back here, what we see is that, let us look at, so let this point be P, and let us look at the triangle PO1 O2. PO1 O2, then we see that this side O1P is of length R1, O2P is of length R2, and O1 O2 is obviously of length D/O1 O2. So, this is the triangle that we had drawn on the just a few minutes back, and then we were talking of the angle between this R2 length side of length R2 and this length, this side of length D/O1 O2. So, this is what this angle is what. So, this angle is what we were calling as beta, but then it is not very difficult to find beta, because if we see this is nothing but 90 degrees pi by 2, and this angle was alpha. So, if you look at this right angle triangle here, this is alpha, and therefore, this angle here is pi by 2 minus alpha. Now, if we sum all these 1, 2, 3 and 4, all these 4 angles, we should get 2 pi. So, 2 pi is equal to, so let us start in the anti-clockwise direction, starting with phi. So, phi plus, and then beta plus pi by 2 minus alpha plus pi by 2. So, from this equation what we will get is that this angle beta is equal to pi minus phi plus alpha. Now, if we see this, let me draw this triangle over here. So, this is beta, this is R1, R2, and this is D/O1 O2. So, if we apply the cosine law on this triangle, what we will get is cos, exactly what we had written here, but then we have shown just on the previous slide that beta is equal to pi minus phi plus alpha, and therefore, cosine of beta is nothing but cosine of pi minus phi plus alpha, which is nothing but, so cosine of beta is equal to cosine of pi minus phi plus alpha, which equals minus of cosine of phi minus alpha, and we get a negative sign here. So, I mean, so this is equal to this, which basically means, so from this we will get this equation. So, what we have here is basically that, so this equation here that we got is nothing but the cosine law applied to this triangle O1 O2P. Now, from the triangular inequality, so what we have is that if this condition is true, then in that case the two circles will intersect at 2 points. So, this is the point of intersection P, and we have this triangle here O1 O2 P, and for this triangle the triangular inequality must get satisfied. And since the triangular inequality must get satisfied, it must be true that d O1 O2 must be strictly less than R1 plus R2. Otherwise, we cannot have a triangle. On the other hand, if we know that so this is one thing. The other thing is that, so this is one condition that we get because of the triangular inequality. But this is only one of the because totally we will be having 3 inequalities. So the other triangular inequality is when we put R1 on the left side and we say R1 is less than d O1 O2 plus R2. R1 minus R2. Now, in this case, since without loss of generality R1 is greater than R2, so this is nothing but the same as its absolute difference, because R1 is, so this is true because R1 is greater than R2. So, therefore, this second triangular inequality implies this. And the third triangular inequality will not give us anything meaningful, because the third will be R2 is less than d O1 O2 plus R1, which is anyways true because R1 is greater than equal to R2 and the distance between the two centers is positive. So, this will not give us anything meaningful. So, what we saw was that if the right hand side of this triangular of this equation here is, if the absolute value is less than 1, then we argued that there will be 2 points of intersection, and then we also showed that using we showed that this equation corresponds to the cosine law for one of the triangles in the first figure, and then applying the triangular inequality to that triangle, we have showed that these two conditions must be satisfied. If the two circles are intersecting at 2 points, then this must be true. So, we have shown only one way implication, that if the two circles intersect, then these two should be satisfied. But the reverse is also true, because if these two conditions are satisfied, this third condition is anyways true, because R1 is greater than R2 and the distance between the centers is positive, and therefore, therefore, we have 3 numbers, 3 positive numbers R1, R2 and d O1 O2, which satisfy all the 3 triangular inequalities, and therefore, they must, one can always construct a triangle with R1, R2 and d O1 O2 as its side. And then we can just take the argument backwards, and if we take the argument backwards, it is not very difficult to show that they are in the two triangles will intersect, and they will exactly intersect at this point P, because since these 3 numbers R1, R2 and d O1 O2 satisfy this triangular inequality, a triangle must exist with 2 of its vertices as O1 and O2, because d O1 O2 is nothing but a distance between the two centers, right, and with another vertex whose distance from O2 is R2. So, this vertex must lie on the second circle, because the radius of the second circle is R2 and the distance of this point P is R2. So, this point P must lie on this circle, and similarly, since this other the third length is R1, the same vertex of this triangle P must also lie on the first circle, and therefore, since it lies on both the circles, this has to be a point of intersection. So, let me again repeat the other argument. So, what we firstly showed was that using triangular inequality, we showed that this condition implies that these two must hold. Now, we will show the backward argument, that if we are only given these two conditions, then also these two conditions will imply that the two circles will intersect. That is because if we are given these two conditions, this condition is anyways true, because R1 is greater than equal to R2, R1 is greater than or equal to R2, and the distance between the centers is positive. Now, given these three conditions, we realize that these three conditions are nothing but the triangle, they seem to be the three equations of triangular inequality. So, we basically have three numbers, three positive numbers R1, R2 and D over O2, which satisfy the triangular inequality, and therefore, we must be able to construct a triangle whose the sides have length R1, R1, R2 and D over O2. Now, D over O2 is nothing but the distance between the two centers. So, we choose two of the vertices of this triangle that we are constructing to be O1 and O2. And the third vertex, we can choose it to be a point which is at a distance of R2 from the center of the second circle, and at a distance of R1 from the center of the first circle. But then we know that the radius of the second circle is R2, and therefore, this point must be on the second circle. Similarly, we know that the radius of the first circle is R1, and therefore, this point must also be on the first circle, and since it is on both the circles, it must be the one of the points of intersection, which means that the two circles are intersecting. So, what we have so far shown in this lecture is that if the two circles intersect at 2 points, so what I mean to say is that if there are two distinct solutions or two distinct solutions of phi to this equation, which will happen only when this right hand side has absolute value less than 1. So, if we assume that condition, that if the right hand side here has absolute value less than 1, in which there are two distinct solutions of phi, which basically means that we are assuming that the two circles intersect at two different points. So, if the two circles, if we assume that the two circles intersect at two different points, then starting from here and using triangular inequality, what we have shown is that the distance between the two centers must be strictly less than the sum of the radius, and also that the distance between the centers must be strictly greater than the absolute difference between the two radius. And then after that, we also showed the reverse argument. We showed that if we start with the assumption that the distance between the two circles is less than R1 plus R2, and it is greater than the absolute difference between the two radius, if we start with that assumption, then also we argued that it must be and maybe in the first 15-20 minutes of the next lecture, we should be able to finish the remaining arguments. So, what the remaining cases are basically the cases where we have the absolute value to be equal to 1 or the absolute value to be greater than 1, for example. So, we will take those cases in the next lecture. So, we will finish that in the first 15-20 minutes of the next lecture, and the remaining part of the next lecture we will start a new topic on family of circles. Thank you.